reason is the first I told you, when the acting moment is more than the capacity of the section, obviously you'll have to go for a doubly reinforced section, or you have to change the dimensions. The second is, what was the second? Anyone? I've just discussed all the reasons when we go for a doubly reinforced section.
The dimension of the beam is to be restricted.
I hope everybody is paying attention to what I'm saying, because this might also come in the exam as a question. Under what conditions you go for a doubly reinforced section? So this question can be asked in the question number 1, compulsory question. I just told you, I think 4 to 5 reasons I told. The first one is when the acting moment is more than the capacity of the section. Second is when the size of the beam is restricted due to architectural or constructional reasons. Is that clear? And then anyone after that what I said?
For continuous beams.
Yes. I hope I'm audible to everyone. You can just unmute yourself and answer. So you did not understand or you did not pay attention. When there is reversal of bending moment, like in underground water tank, in that case also we go for a doubly reinforced section. And when there is shock or impact load acting, at that time also we can go for a doubly reinforced section. So these are the reasons or the conditions under which we go for a doubly reinforced section. I hope this is clear. What is a doubly reinforced section? What is the significance, or when do we go for a doubly reinforced section? Is that clear, everyone? So now we can start with the equations which are used in doubly reinforced section. So shall we go for the equations? This is clear, whatever I said so far? Just tell me yes or no. Whatever we have discussed so far, is that clear? Yes, I think you can unmute yourself.
Yes, sir.
Right? Or is there a problem to unmute yourself?
No, sir.
Okay, so whenever I'm asking questions, so you can just unmute yourself and give me the answer. Okay.
Okay, sir.
So can we proceed to the equations now? So just give me a moment. I'll share my screen and then we can start with the equations. So is my screen visible to everyone?
Yes, sir.
Okay. So now we'll start with the derivation of equation. We'll just go through the equations like we had in singly reinforced section. So now we can see the equations in doubly reinforced section. So you can see here we have considered a doubly reinforced section of width B and effective depth D as shown below. So this is the cross section of a beam. Okay, so this is the width of the beam and this is the overall depth D. So since it is doubly reinforced, I have shown the reinforcement, the bottom as well as the top. So now first let us understand this stress diagram for a doubly reinforced section. Okay, so this is the equivalent stress diagram which we have already seen in singly reinforced section. Correct? So equivalent stress diagram you already know. So I've just drawn the equivalent stress diagram. So this is sigma CBC and this is sigma HT by M, equivalent stress. And this is the neutral axis at a distance X from the top fiber. And this is the lever arm D minus X. Okay. So in this, what is the difference? So let us compare this with the singly reinforced. So in the singly reinforced, we had this C. Okay. So the distance of this force from the top fiber is X by 3. This we already know, and this is d minus x by 3. Now what is the difference? What is the major change here? So you can see here at the level of steel, the compressive steel, you will have some stress. So that is given as sigma dash CBC. And again for this compressive steel, you will have some force which is given by C2. So basically in this we will have two forces, C1 and C2. And this distance from the top to the center of the compressive steel is given by D dash. Okay, so the distance from the top fiber to the center of the steel is given by D dash. I hope this diagram is clear to everyone. And this lever arm for the compressive force C2, the lever arm is D minus D dash. Okay, so now here we will see the various components, the terms. So B is the width of the beam, D is the overall depth of the beam, small d is the effective depth of the beam, and D dash. So what is D dash? I have just told you, it is the effective cover in the compressive zone. Okay, so that will be denoted by D dash. And what is AST? AST is the area of steel in the tension zone, and ASC is the area of steel in the compression zone. Now what is sigma dash CBC? So sigma dash CBC is compressive stress in concrete at a depth D dash from the top. Okay, so here you can see sigma dash CBC. I hope this is visible to everyone, or should I zoom it more? So here you can see sigma dash CBC is the compressive stress in concrete in the compressive steel at a depth D dash from the top. And what is C1? C1 is the compressive force in concrete. And what is C2? C2 is the compressive force in steel, that is ASC. So total C will be given by C1 plus C2. Is that clear, everyone? So you can make a note of this. So stress diagram for a doubly reinforced section. So you can make a note of this, or shall I proceed? Yes, shall I proceed, or you're making a note of this?
So we are making a note.
Okay, okay. So I think you have noted this. So now let us move ahead. So in this doubly reinforced section, basically three formulas are used. So I have just written down for you all the three together. So this is the first equation, b into x by 2 plus 1.5 m minus 1 into AC into x minus d dash is equal to m into AST into d minus x. So this equation is normally used to find out the neutral axis. The second equation is the equation for finding out the moment of resistance, which is given by b into x into sigma CBC by 2 into d minus x by 3 plus 1.5 m minus 1 into AC into this is sigma dash CBC into d minus d dash. And the third equation is used to find out the ASC. Okay, so these are the three equations which we will use in doubly reinforced section. So now we will also see how these equations have been arrived. Okay. So now let us move on to the next slide, the next page. So now
Then let,
again,
then let us write the formulas.
okay, so you're still writing.
Sure, so shows the formulas.
The formulas.
Okay. So I think everyone has noted down the formulas also. So now let us see how these formulas have been derived. So by looking at this formula, I think you have already understood that this we have already used in singly reinforced section also to find out the neutral axis. Okay. So how did we find this formula in singly reinforced section? Anyone remembers? They can just tell me if anyone remembers. To find out the actual neutral axis, we used what condition have we used in singly reinforced section? See, MR basically it is given
C
by,
is equal to T.
yes, anyone?
So total compressive force is equal to total tensile.
Total compressive force is equal to total tensile force. Are you sure? One more thing we had used, moment of area on compression side is equal to moment of area on tension side. Remember? So the same thing we have used here. Moment of area on compression side is equal to moment of area on tension side for the first equation. The second one is the MR. So MR, since you know here there are two forces C1 and C2. So MR is given by C1 into lever arm plus C2 into lever arm. Okay, so in singly reinforced section we had only C into lever arm, but here it is C1 into lever arm. This is the first term plus C2 into lever arm. This is the second term. Is that clear? So now let us see. I hope everyone has written these three equations. Let us see how to find out this. So first we'll find out the neutral axis. Okay. So the neutral axis, we have the critical neutral axis and the actual neutral axis. So critical neutral axis is always given by this equation, remember. Okay. So this will never change. Sigma CBC upon sigma ST by M is equal to XC upon D minus XC. Okay. So now coming to the actual neutral axis. So from the equivalent stress diagram, we have seen that neutral axis is situated at the CG of the given section. So from that we can imply that the moment of area on the compression side is equal to moment of area on the tension side. Okay. So now what is moment of area? It is area into distance. Okay. So normal moment is force into distance, but moment of area is area into distance. So similarly, moment of area on the tension side is equivalent area of concrete into distance of the CG of the steel from the neutral axis. So now here area is, if you see the compression zone, what is the area? B into X, and the distance of the CG is X by 2. Correct? So from that area, we have subtracted the area of steel. So that is again area into distance of CG from the neutral axis. So what is area into distance of CG from the neutral axis? If you see this figure, this is X minus D dash. Okay. So this total X minus this is D dash from the top. And now this, okay, so this portion is given by a clause in the IS code. Okay, so this is the addition. So this is given by IS code. So IS 456 in 1978, it is given that the compression in the bars where the compressive resistance of the concrete is taken into account shall be the calculated stress in the surrounding concrete multiplied by 1.5 times the modular ratio. Okay, so this is given in IS code 1.5 times the modular ratio into the area of the compressive resistance. So that we have taken as per the IS code. So this is the addition part. So this we did not have in singly reinforced section. So this is added 1.5 m into AC into x minus d dash, and the equivalent area of concrete is nothing but m into AST, and the distance is d minus x. So now if you calculate this, if you evaluate this, you will get, so this 1.5 m into ASC minus ASC into x minus d dash. So this is common, ASC into x minus d dash. So common is taken out. So what is remaining? 1.5 m minus 1. So this is your final equation to find out the actual neutral axis in doubly reinforced section. So b into x by 2 plus 1.5 m minus 1 into ASC into x minus d dash is equal to m into AST into d minus x. Is this clear, everyone? So this derivation is not asked in the examination, but just I'm explaining you how the equations have been derived. We can directly start with the numericals, but still it is better that you know the equations, how they have been derived, and then we'll start with the numericals. Is that clear, everyone? So you can just reply me by unmuting yourself whenever I'm asking you something so that we can proceed. Any doubt in this? Shall we proceed?
Yes, sir. Proceed.
Yes, what about others? They are still writing, or shall we proceed?
We can proceed, sir.
Okay, fine.
Proceed.
So now let us come to the second equation, that is nothing but moment of resistance. So this is important, moment of resistance. So here you can see I have drawn the stress equivalent stress diagram again. So it is the same thing. This is x from the top fiber to the neutral axis. The distance is x. This is d minus x. This is the tensile force. This is the compressive force C1 and C2. Sigma CBC, sigma dash CBC. This is x by 3, and the lever arm distance is d minus x by 3. So this is clear. So moment of resistance is calculated by taking the moments of forces about the CG of the tensile steel. So remember this. So if you remember this, by to remember the equations, it will be easy. So MR is calculated by taking the moments of forces about the tensile steel. So now let us see how the MR equation has been derived. So moment of resistance is given by moment of the compressive force in concrete about the tensile steel plus moment of equivalent concrete force about the tensile steel. So that is C1 into lever arm 1 plus C2 into lever arm 2. So what is C1? C1 force. What is force? Force is equal to area into stress. Is that clear? Force is nothing but area into stress. This we have already seen. So this is the area of the compression zone. If I just hatch this, so B into X is the area of the compressive zone. And this is the stress, average stress 0 plus sigma CBC by 2. And what is the lever arm? D minus X by 3 for C1 plus, now for C2, this is again which we have already done, 1.5 m minus 1 into ASC into sigma dash CBC is the stress for C2, and the lever arm for C2 is D minus D dash about the tensile steel. Is that clear? So just you have to remember this 1.5 m minus 1 into ASC. So what is C2 is again nothing but area into stress. So area is given by this total area 1.5 m minus 1 into ASC, and stress is nothing but at this point it is sigma dash CBC, area into stress into lever arm. So if you remember this, it will become easy for you to remember the equation. Okay, so even though if there is no need to just mug up the equation, if you understand how this has been derived, so it becomes easy for you to understand or remember the equations. So this is C1 into lever arm plus C2 into lever arm. C is nothing but area into stress. So if you remember that, so this is area and this is stress, and lever arm is nothing but, from the equation you know, it is d minus d dash. Is this clear, everyone? Moment of resistance clear है अभी? Yes. So you have to answer whenever I'm asking something. This shows that whether you're paying attention or not, or listening or not.
Yes, sir.
So the moment of resistance equation is clear. So now we will go for the third equation. So now remember here, sigma dash CBC we don't know. So that you have to find out. So this sigma dash CBC is given by the equation sigma CBC into x minus d dash upon x. And I told you 1.5 m minus 1 into AC is equivalent concrete area of the compression steel. So this is the equivalent area. So now this sigma dash CBC, how this equation is arised? Again, this is by similarity of triangle. So if you take this triangle, this is sigma CBC upon x, sigma dash CBC upon this distance, x minus d dash. Okay, so again, if even though if you don't remember, you can just look at the stress diagram and find out sigma dash CBC. But after solving some problems, I think you will remember the equations. So don't worry, it seems big, but if you understand and do a couple of problems, then it becomes easy for you to remember the equation. So sigma dash CBC is sigma CBC into x minus d dash upon x. And this one more equation is there, sigma SC. This is the stress in the compressive steel, is given by 1.5 m into sigma dash CBC. Okay, so this you have to remember. So now let us move to the last equation, that is to find the compressive steel. This is the equation. So what we have done, we have equated moment of equivalent area of tensile steel with the moment of equivalent area of the compressive steel. So this is given by m into AST about the neutral axis. So that's why d minus xc, and moment of equivalent area of the compressive steel is 1.5 m minus 1 into ASC into xc minus d dash. Okay, or x minus d dash. So this is the last equation to find out the ASC. So the first equation is used to find out the actual neutral axis. The second equation is used to find out the moment of resistance MR, and the third equation is used to find out the area of compressive steel. So we have seen how all these three equations have been derived. I hope this is clear to everyone. So shall we move ahead, or you're writing this?
Writing, sir, writing.
Sir, writing.
Okay, so quickly write down the equations. We have to start the numericals also. So since you already know that design subject is, it's a very vast subject, so you have to be a bit quick.
Hello, sir.
Yes,
Sir, I didn't understand the third equation.
the third equation. Okay, so third
Please
equation I have already written here.
wait.
So moment of equivalent area. So when you equate moment of equivalent area of the tensile steel about the neutral axis with the moment of equivalent area of the compressive steel about the neutral axis, by equating this, you will get the equation which is used to find out the compressive steel, that is ASC. So moment of equivalent area of tensile steel is nothing but M into AST. This is, and about the neutral axis, जो tensile steel है, about the neutral axis से distance क्या है इसका? That is d minus x. See here, ये जो distance है neutral axis से tensile steel का distance कितना है? D minus x. So that is written here, d minus x. So equivalent area of tensile steel is M into AST, and about the neutral axis means that distance, that is d minus x. Now similarly, moment of equivalent area of compressive steel. Equivalent area of compressive steel क्या है? 1.5 m minus 1 into ASC, correct? And this distance from the neutral axis, इसका distance from the neutral axis कितना है? That is total x minus d dash. ये total x है और न्यूट्रल एक्सिस से डिस्टेंस चाहिए, तो d dash माइनस करेंगे, so that is x minus d dash. Is that clear now?
सर बट C1 क्यों नहीं लिए?
Sorry,
सर वो कंप्रेशन स्टील लिए, कंप्रेसिव कंक्रीट का नहीं लिए.
which force is not taken, you are asking?
C1 फोर्स.
C1 force, C1 force is singly reinforced section के लिए यूज होता है ना ये. अभी जो एडिशनल ऐड क्या हुआ है, ड्यू टू ASC सिर्फ C2 ऐड हुआ है, बराबर. कंप्रेसिव स्टील के लिए एडिशनल क्या है इसमें, अपार्ट फ्रॉम व्हाट वी हैव ऑलरेडी सीन इन सिंगली रिइंफोर्स, C2 है, तो ASC फाइंड आउट करने के लिए सिर्फ C2 लेंगे. अंडरस्टूड?
Okay, yes, understood. This is additional steel to balance the
टू
compressive steel.
बैलेंस द कंप्रेसिव फोर्स, जो रिमेनिंग मोमेंट जो बैलेंस हो रहा है. अभी सपोज मेरा मोमेंट का कैपेसिटी है, एक पर्टिकुलर सेक्शन का कैपेसिटी है और जो एक्टिंग मोमेंट है उससे ज्यादा है, सपोज 100 है मेरा कैपेसिटी और एक्टिंग मोमेंट है 125, तो अभी बैलेंस मोमेंट कितना है? 25, करेक्ट. तो उस 25 के लिए मैं सिर्फ ASC निकालूंगा. So that we will see in the design part when we do the third type of the problem. So then you will understand. So we have only taken the C2 force to find out the ASC. Understood?
Yes, sir.
Okay. So I hope everyone has noted down this. So now we can start with the numericals. Shall we start with the numericals now? Or anyone has any doubt? So you can write in the chat box or you can just say, then I'll just go ahead. Yes, shall we go ahead for the numericals? Okay. So now we will see the numericals. We already know that there are three types of numericals: to find out the MR, to find out the stresses, and to design the section. So quickly just write down the procedure for the first type. Okay. So these are the three types: to find MR, to find stresses, and design of the section. So first we will start with the type 1, that is to find out the MR. So the first step is to find out the critical neutral axis, then find out the actual neutral axis, then compare X and XC, and then find out MR. Okay, so one thing you have to remember in this, as you can see in the step, for under reinforced section, sigma ST is known. Okay, so when you compare this, you will come to know whether it is under reinforced or over reinforced. Correct? So once you know that it is an under reinforced section, suppose it is an under reinforced section, that means steel will reach its permissible value first. So that means your sigma ST is known. Okay, and then you have to find out sigma CBC, sigma dash CBC, and so on. And remember, if actual sigma SC is less than permissible, then take the actual value. अगर ये permissible से ज़्यादा है तो take the permissible value, and then find MR. So similarly for over reinforced section, sigma CBC is known. Correct? Over reinforced section में क्या होगा? Concrete will reach its permissible value first. So sigma CBC is known. We will take the value of sigma CBC and then we will find out the other unknowns and then MR. So quickly make a note of this. When we solve the problem, you will understand.